Inventory modeling. In this unit, we will discuss managing inventory for an operation. We start by understanding the types of demand, independent and dependent. Our goal is to have the right amount of inventory to supply customers while minimizing our cost. To balance these needs, we will use different inventory models based on different operational situations. The economic order quantity model will be defined along with its associated limits and calculations. The reorder point will be defined followed by the production order quantity model with its requirements and steps. Finally, we will look at the case where the supplier offers quantity discounts and when demand varies with a given probability distribution. We start by defining demand types. Independent demand is not tied to other items in inventory. Think of customer demand for finished goods. Dependent demand is tied to the demand for another item in inventory. Think of 4 tires of dependent demand for every car independent demand that is purchased. There are several costs associated with inventory. Holding cost or carrying cost is due to the storage of the item. Think of warehouse space, shelving, lift trucks, and personnel. Ordering cost occurs every time an item is ordered from a supplier. Finally, setup cost is a manufacturing cost incurred every time the factory sets up to make a certain item. Setup cost is usually proportional to the setup time. To achieve the proper balance and lowest costs, we analyze our independent demand to determine how much material to purchase based upon setup, ordering, and carrying cost. This is the EOQ, or economic order quantity. We will also look at the production order quantity, POQ model, and the quantity discount model. The basic EOQ model has several assumptions that are not always applicable in real life, but act as a starting point. Demand must be defined and constant with a known lead time for purchased items. Once delivered, inventory is immediately available. Here we see the expected sawtooth model of inventory quantity in stock over time. When new material, quantity Q, is received, inventory jumps up to that level. Inventory is gradually used at a constant rate until fully depleted. The average inventory on hand is simply Q divided by 2. Recalling our earlier discussion on costs, we see that setup order cost per unit drops as the quantity increases. At the same time, the holding cost goes up as the inventory held goes up. Combining the holding cost and setup cost, we get a total cost curve that dips in the middle. The lowest point represents the optimal order quantity and the minimum total cost. To minimize our costs, we order the quantity Q star each time an order is placed. Summarizing our EOQ cost analysis, we see that minimal total cost occurs when the holding cost and setup cost for a given quantity are equal. Ordering more or fewer items than Q star will increase total cost. Let's look at the EOQ equation. We start by defining the equation for annual setup cost. The variable definitions are listed here. Notice that the length of time considered for each variable value must be the same. We look at annual demand and annual carrying cost. If our starting point uses different lengths of time, one or the other must be converted. Annual setup cost equals the annual demand divided by the quantity per order times the setup cost per order. Now we calculate the annual holding cost, which equals the order quantity divided by 2 times the holding cost per unit per year. We determined earlier that the lowest cost is found when setup cost equals holding cost. Equating the equations of the two costs, then solving for Q star, we find that the economic order quantity Q star equals the square root of the quantity 2 times the annual demand times the setup cost divided by the annual holding cost. For this example, we substitute the values into the equation and find an economic order quantity of 200 units. This will be the quantity ordered each time. Note that the demand and holding cost are annualized. Based on the previous calculation and the resulting economic order quantity of 200 units, we want to determine how many orders will be placed annually. This equation is number of orders N equals the annual demand D divided by the economic order quantity Q star. Substituting the known values, we determine that 5 orders will be placed each year. Now we find the time between orders. The equation has the time between orders T equal to the number of working days per year divided by the number of orders. For this example, we assume 250 working days per year. This is 5 days a week over 50 weeks. The result shows 50 days between orders. Finally, building upon the example, we determine the total annual cost, which we recall is the sum of the setup cost and the holding cost. Again, substituting the values into the equation for setup cost and then holding cost, we get $50 of setup cost and $50 of holding cost for a total annual cost of $100. In real life, your results are unlikely to come out to such perfectly round numbers, but the analytical process is the same. Now we move to the reorder point. The EOQ tells us how much to order, while the reorder point, or ROP, tells the team when to order the next quantity of material from the supplier. For this calculation, we need to know the lead time, L, how long after placing the order the material will be received. The reorder point calculation is demand per day times the lead time in days. Note here again that the time frame must be the same. Both values must be in terms of days. The equation may also be expressed as ROP equals demand D divided by the number of working days per year times the lead time in days. Graphically, we can look at our sawtooth consumption model discussed earlier. We see that we back up from the needed delivery date when we run out of material. This is the date when the order must be placed based upon the lead time L. Moving up to the curve, the reorder point is found. When the inventory drops to the reorder point, the next order must be placed. Applying the reorder point analysis to an example, we start by defining the problem and identifying the values of the variables. Given an annual demand of 8,000 phones over 250 working days per year, we can calculate the reorder point if we have a lead time of 3 or 4 days. For 3 days, we find a reorder point of 96 units, while a lead time of 4 days gives us 128 units. This ends our look at the economic order quantity model. The production order quantity model is used when inventory increases over time. Instead of receiving a shipment of material from a supplier, we create the product internally. As each item is produced, it is moved to stock. As a result, instead of the sawtooth model of the economic order quantity with a vertical spike of inventory when received, the inventory goes up gradually as replenished. For the blue portions of the curve, we are producing product and adding to inventory while drawing out material to fulfill customer orders. During the yellow portion of the curve, we have finished producing materials and are only drawing stock from the warehouse as needed. Lowercase t indicates the time while we are in production. Now we look at the situation where quantity discounts are available from the supplier. In this example, the base price is $100 per unit. However, if we buy from 120 to 1,499 units, the price drops to $98 per unit. Similarly, order quantities in excess of 1,500 units are at a $96 price per unit. We need to decide if we minimize our costs by taking advantage of these price breaks. The calculation for quantity discount model is shown here. We have added the cost of product to the setup and holding costs. We note that the holding cost is expressed as a percentage of the unit price rather than a fixed cost per item. We see the slightly modified economic order quantity Q star equation. To analyze the value of a quantity discount, we start by calculating the economic order quantity for each of the pricing levels. Next, we determine whether the quantity exists within the valid range for that price discount. This will become clearer when we look at the analysis graphically. Looking at the graph, we see three different total price curves, one for each pricing level, no discount, discount 1, and discount 2. Looking at the top curve, representing no discount, the EOQ falls above the quantity of 120 units. But this is outside of the applicable range, so this is not the answer. For this curve, the lowest cost point is when the curve crosses the 120 quantity vertical line. So the lowest cost, quantity given, no discount, is 120 units. Moving down to the next curve for discount 1, the EOQ falls within the valid range. So the EOQ for discount 1 results in an annual cost of $517,155. This is the best result so far. Finally, we look at the total cost curve for discount 2. Again, the EOQ falls outside of the valid range, and the lowest point of the curve is at the border when it crosses the 1,500 unit vertical. At this point, the total cost is $520,053. Comparing the results from the three curves, we see that the lowest total cost is $517,155 implementing discount 1. All of the methods can be customized to meet specific business needs. Options include discounts for all units, discounts above a threshold, discounts on aggregate demand, and truckload discounts. Next, we review probabilistic models and safety stock. When demand is not certain, we use safety stock to avoid stockouts and maintain a certain service level. The revised reorder point equation is shown here. The difference is that we have added safety stock, SS, to the daily demand multiplied by the lead time. The goal is to minimize inventory while ensuring that the operation does not run out of material while waiting for the next supplier order to arrive. In this case, we establish a range from the minimum to the maximum demand during lead time while waiting for the material to arrive. Since demand varies, we use a normal distribution to predict the values. We start by setting the number of standard deviations we want to consider. The revised reorder point, ROP, is the demand during the lead time plus the Z value times the standard deviation of demand during lead time. The safety stock is Z times delta DLT. We are using a normal curve with a mean of 350 units to predict demand. We first set an expectation that 95% of the time we will be able to meet customer demand. Thus, the risk of a stockout is 1 minus 95%, or 5%. The safety stock level is the quantity of material above the mean necessary to meet this probabilistic service level. In this example, the average and standard deviation of demand along with the service level are given. The z-value may be found in the text and is readily available online. For a service level of 95%, the z-value is 1.645. Substituting the values into the equation, we find that the safety stock is 16.5 kits. Adding the safety stock to the mean demand, our reorder point should be 366.5 or 367 kits. We round up since it is impossible to have partial kits in stock. Key points to remember. We discussed the tools and methods for managing inventory for an operation. We start by understanding the types of demand, independent and dependent. Independent demand is based upon external needs, for example, customer demand for a product. Dependent demand is an internal requirement for a component or subassembly that is part of the final product. Thus, the component demand is dependent upon the product demand. Our goal is to have the right amount of inventory to supply customers while minimizing our cost. We define the elements of inventory cost, including holding cost, ordering cost, and setup cost. To balance these needs, we will use different inventory models based on different operational situations. The economic order quantity model assumes that demand is known and constant. Lead time is known and inventory goes to stock immediately. The equation balances holding cost with ordering cost and calculates the lowest overall cost. At the lowest cost, the order quantity and reorder point are defined. More key points to remember. The production order quantity model is similar to the EOQ, except that material is manufactured internally. As a result, material moves from the internal fabrication center to stock continuously as produced. The goal, as before, is to balance holding costs with ordering and setup costs. The order quantity and reorder point are calculated here again. Next, we look at the case where the supplier offers quantity discounts. For each discount level, we calculated the EOQ to find the volume that results in the lowest cost. The lowest cost for each discount is compared to find the right choice. Finally, we consider the situation when the demand varies with a given probability distribution. In this case, we calculate the necessary safety stock, or extra inventory, to cover the variability to ensure a certain degree of customer service.